Here in Lab 3, we're taking a look at yet another BSCI topic. Specifically in Lab 3, we're going to be configuring BGP in a multi-homed environment. And by multi-homed, I simply mean this. We're going to have a router that's pointing out to a backbone network, and we're going to point out to that backbone network not by pointing to a single router to get us there, but to a couple of routers. There are two ways to get to the backbone network. We call that multi-homing. And in your environment, this may be a couple of internet service providers to take you out to the internet. Or as we have in our situation, we have a couple of routers on the corporate backbone that will get us to that network. And if one router is down, the other router is ready to step in and start routing us to the corporate backbone. Specifically, here are the objectives we have in this lab. First up, we want to configure eBgp neighbors. We want to set up Bgp peers with routers in different autonomous systems. That's what eBgp means. That's exterior BGP. We also want to specify a network that we want advertised via the BGP process. Then once we have this basic core BGP configuration in place, we want to verify our configuration. We want to take a look at a show command. We'll issue this command on various routers to make sure that the peering relationships are set up correctly. And for the router that's multi-homing out to the corporate backbone, we'll see that it has a couple of different options, a couple of different paths to get out to that corporate backbone. And we may discover it's not using the optimal path. We might have to fix that. Next up, we want to take that information learned from the corporate backbone and redistribute it into RIP version 2. In our scenario, we have a small remote site with a couple of routers. Those routers are running RIP version 2 between themselves, and we want to take the backbone network learned via BGP and redistribute that into RIP version 2. And then finally, you might recall that I mentioned that as we're doing this multi-homing, we might, by default, not be using the optimal path. How can we fix that? Well, there are different ways of fixing it, but what we want to do is this. We're going to manipulate the autonomous system path as advertised by BGP. Before we get into the router configuration screen, though, let's do this. Let's first take a look at our topology that we're working with. Notice we have a couple of backbone routers, BB1 and BB2. They're interconnected with the backbone network that we want to be advertised throughout our network, network 10.1.1.0 with a 30-bit subnet mask. We also have a remote site. At this remote site, we have a couple of routers, R1 and R2. Now notice that R1, it's multi-homing. It's pointing to two different routers on the corporate backbone. But within that site, it's speaking RIP. Specifically, it's speaking RIP version 2 over to router R2. And just because we have a couple of different paths to get out to the corporate backbone, that's no indication that these paths are created equal. Let's take a look at the bandwidth available via these two different paths. If we go from R1 to BB1, that link is currently running at 1 megabit per second. However, if we travel the path from R1 up to BB2, that's running at 2 megabits per second. Well, obviously, from our perspective, we would prefer to use the route that goes from R1 to BB2. But we may discover that's not what BGP is doing by default, and we'll see how to overcome that default behavior. Let's take a look at the syntax we're going to be using to set this up. First, we'll want to visit all the routers that are running BGP, specifically BB1, BB2, and R1. On those routers, we will want to enable the BGP routing process with the command router BGP followed by an autonomous system number. The autonomous system numbers, by the way, were on that previous diagram that we just saw. This command takes us into router configuration mode. It's from router configuration mode where we can do things such as specifying the network that we want to advertise inside of this BGP process. We can do that with the network command and optionally specify a mask, which is a subnet mask, not a wildcard mask. Then we also want to point to our neighbors. We need to form these Bgp peering relationships. We can point to a neighbor with the command we see on screen. We can say neighbor followed by the IP address of that neighbor, followed by the keyword remote-AS, remote autonomous system, followed by the autonomous system number that neighboring router belongs to. That's our game plan. Let's now go out and take a look at the configuration. Let's start off on router BB1. On router BB1, let's go into global configuration mode with the configure terminal command, and now let's enter router configuration mode. Let's say router BGP, and we follow that with the autonomous system number. Based on our topology, that's going to be autonomous system number 65002. Now let's form our BGP neighborships. Let's say neighbor, give the IP address of one of the neighboring routers. We'll say 10.1.1.2, and that router, which by the way is router BB2, that is in autonomous system 65003. We specify that with the remote AS 65003 command. We have another neighbor, router R1, sitting at that remote site in our corporate network. Let's form a neighborship with that as well with the command neighbor. In this case, it's 172.16.1.2. And that router, router R1 in our topology, it's located in autonomous system 65001, and I abbreviated remote AS. The network that we want to be advertised via BGP is the network that is interconnecting our backbone routers. In our example, it's going to be network 10.1.1.0, and we're not using a natural mask. We're not attempting to advertise the entire 10 dot network. So we specify the optional keyword of mask followed by the subnet mask, the 30-bit subnet mask that we're using. We'll say 255.255.255.252. I think we're done now on router BB1. Let's hop over now to router BB2 and continue our configuration there. We need to do a mirror configuration. We're doing essentially the same thing over on router BB2. We first go into global configuration mode. We're then going to say router BGP followed by router BB2's autonomous system number, which is 65003. We again form our neighborships. We say neighbor, and we have a neighbor at 10.1.1.1. That's router BB1. That router, as we saw previously, is in autonomous system 65002. We also have a neighbor down at the remote site, router R1. That neighbor, it has an IP address of 172.16.2.2. Its autonomous system number is 65001. We also want to advertise the 10.1.1.0 network from router BB2. We do that with the network command. We say network 10.1.1.0, and again we'll specify that optional mask of 255.255.255.252, and now we're done on router BB2. Let's finally, to set up our core BGP configuration, let's go over to router R1. Again, imagine that router R1, that's the router sitting at one of our remote branch offices. It's multi-homing back to the corporate backbone. It's got a couple of BGP connections getting out to the corporate backbone. From router R1, we again go into global configuration mode, and we're going to say router BGP 65001, the autonomous system of router R1. Let's set up those neighborships again. We'll say neighbor 172.16.1.1 to point to router BB1. It's in an autonomous system of 65002. And now we need to form a neighborship with router BB2. It has an IP address of 172.16.2.1. And router BB2, it is in autonomous system 65003. At this point, we should have all of our core BGP configurations complete. There are no routers we want to advertise from the perspective of router R1, so there's no need to enter the network command. We're simply trying to learn that backbone network from routers BB1 and BB2. To see if we have formed these neighborships, we can give this command. Let's go out to privilege mode, and let's say show IP Bgp. Let's see if those neighborships have been set up just yet. Now currently, it says that they have not been set up. If we wait just a few moments, I think we just had a change. Take a look at this. It says that neighbor 172.16.2.1, it just came up. That's good news. Let's reissue that show IP Bgp command again. Here we go. I think we're in great shape now. We now have a couple of neighbors. We have router BB1 and router BB2. Now, 172.16.2.1, that's BB2. That's the path that we would prefer to take. You might recall that's the path over which we're traveling on a 2 megabit per second link. Now, 172.16.1.1, that's the path to router BB1. It's a great backup path, but the link going to router BB1, it was only running at 1 megabit per second. So the question comes up, which path are we using? Are we pointing to BB1 as our default route or BB2? Here's the clue. You see this greater than sign? This greater than sign is telling us the quote-unquote best path according to the BGP routing process. Why is that? Well, all things being equal as they are in this case, the BGP is not going to be considering the bandwidth. It's going to look to things such as, how many autonomous systems do I have to pass through in order to get to this network? We could also set up things such as the multi-exit discriminator, the local preference, different ways that we could influence this. But with this default configuration, we're going to be choosing the router, either BB1 or BB2, that has the lowest router ID. What determines what the router ID is of one of these routers? Well, in this scenario, the router IDs are the IP addresses assigned to the loopback interfaces of these routers. If I do a show IP Bgp command, we're going to see information for this router that we're on right now. We're being told that this router has a router ID of 3.3.3.3. If we look at our neighbors, if we say show IP Bgp neighbor, we can see the router ID of our neighboring routers. Notice the router ID of 1.1.1.1, that's router BB1. That number happens to be less than the router ID for our other neighbor, which is 2.2.2.2. That's router BB2. So we're not taking the optimal path at this point. That could be a concern. We'll come back and revisit that in just a few moments. For now, though, let's, on router R1, redistribute the routing information that we've learned via BGP into the RIP process. Let's make sure that it's there, first of all. Let's do a show IP route on router R1. Everything is looking good from the perspective of router R1. We have learned via BGP about network 10.1.1.0. Notice our next hop address. Our next hop address is BB1. Not the optimal path in our opinion, but we'll have to fix that. By the way, but before we do this redistribution, I suppose it would be a good idea for us to visit our other BGP routers, and let's just make sure that their neighborships have formed correctly as well. So let's do that. Let's go over to router BB1 first of all. Over on router BB1, let's say show IP Bgp. Show IP Bgp tells us that we have knowledge about network 10.1.1.0. That's great news. We've learned that from BB2, but we also know about it internally. Notice the next hop address is all zeros. Interesting. Let's do this. Let's do a show IP Bgp neighbor, and we'll take a look at the neighborships we formed. Looks like we have a neighborship with BB2. And if we scroll down just a bit, we see that we also have a neighborship with router R1. All that is great news. Everything looks to be up and happy. Let's jump over to router BB2 and make sure its configuration looks good as well. Let's get over on router BB2 and let's issue that command once again. Let's issue the command show IP Bgp neighbor. And sure enough, router BB1 is a neighbor. That's great news. And if we scroll down, we can see that router R1 is a neighbor as well. Great. I think the BGP core network is configured. At this point, we want to take this backbone network, the 10.1.1.0 network, and redistribute that information via RIP version 2, into this remote site. To do that, we go over to router R1. From router R1, let's do this. Let's go into global configuration mode. Then let's go into router configuration mode for the RIP version 2 process and set up redistribution. We say redistribute BGP routes. Specifically, BGP routes that are known to this autonomous system 65001. And when we do this, how do we want this to appear in RIP? Remember what RIP uses as a metric? It uses hop count. How many routers do we have to pass through in order to get to this network? Well, in our topology, let's do this. Let's say that the metric is going to be a 2. We will advertise that we can reach this backbone network in only 2 hops, which is accurate for our network. I think we're done on router R1 right now. Let's go over to router R2. Remember, this is the other router at our remote site. Let's see if router R2 has knowledge now about how to get to that backbone network, how to get to the 10.1.1.0 network. From router R2, we say show IP route. Look at this, great news. We learned it via RIP due to the redistribution that we did, but we do know via RIP how to get to the 10. network. There is one issue that we need to solve, though. Remember what we were saying earlier? We were saying earlier that we weren't choosing the optimal path. We weren't really using an optimal path when we were going out to our backbone network. Let's examine why that might be. What we're doing is we're advertising the number of autonomous system hops that it takes to get from router R1 up to the backbone. And in our scenario, routers BB1 and BB2, they are each telling router R1 that it can get to this network, the 10.1.1.0 network, with only 1 autonomous system hop. Router BB1 is saying, send your traffic to autonomous system 65002, and router BB2 is saying, send your traffic to autonomous system 65003. Here's what we can do to influence BGP's decision, however. Because at this point, everything appears to be equal, so we're simply going with the lowest router ID. What we can do is something called an autonomous system prepend. From router BB1's perspective, when it sends out a BGP advertisement to router R1, it's going to be exaggerating a little bit. It's going to say, in order to get to me, instead of just going through 1 autonomous system, which is 65002, you're actually going to have to go through a couple of autonomous systems. 65002 followed by 65002. I know it doesn't make sense going through the same autonomous system twice, but router R1 doesn't care. Router R1 isn't looking at the autonomous system number. It just says, okay, looks like I have to go through 2 autonomous systems. That doesn't sound so good. That's what we're going to do. We're going to make it appear less desirable to go to the backbone via BB1. Meanwhile, BB2 is going to continue to advertise, yeah, I can get you to the backbone network if you'll simply send traffic into autonomous system 65003. You see how doing this makes BB2 look much more attractive? Here's the syntax we're going to use to set this up. We're going to use something called a route map. To get into route map configuration mode, we simply say from global configuration mode, route-map followed by the name of the route map. Once we're in route map configuration mode, lots of things we can do from here, but for our purposes, it's pretty simple. We're going to use the command set ASPath prepend followed by an autonomous system number. We're going to say that we want to prepend, we want to add an additional autonomous system to the autonomous system path being advertised. How do we then tie this information? How do we tie this route map to the BGP process? Very simple. We go back into router configuration mode for that BGP autonomous system, and we say neighbor, followed by the IP address of our neighbor, the IP address of R1 in this case. Then we say route-map, followed by the route map name, followed by the keyword of out. As we're sending BGP updates out to that neighbor, we're going to say that it's going to take a couple of autonomous systems to get to this network. Let's go back out to our interface and see how to set this up. Let's go back to router BB1, because router BB1, that's the one that's going to be sending out these route updates. We need to tell router BB1 to do the autonomous system prepend. Here's how we do that. Sitting on router BB1, let's go into global configuration mode and create a route map. Let's say route-map, and let's give it a name AS path for autonomous system path. Now that we're in route map configuration mode, let's give the command set AS-path prepend, followed by the autonomous system number that we want to prepend to this autonomous system listing that we have to go through to get to this specific network. We say set AS-path prepend 65002. At this point, we have created a route map, just a couple of commands. To tie this route map configuration to our BGP routing process, we go back into router configuration mode. We say router BGP, followed by the autonomous system number, which is 65002. And we say for the neighbor that resides at IP address 172.16.1.2, router R1, we want to apply the route map that's named AS path, and we want to do that in the outbound direction. When we are sending route updates out to our neighbor, we want that route map applied. Something you might notice with BGP, after we apply a policy such as this, it might take some time for that policy to be propagated to that neighbor. Let's see how we might be able to speed that up just a bit. We can perform what is called a soft reconfiguration. We're going to say clear IP BGP, and we're going to give a wildcard of a star, and we'll say soft out. What this does, this allows policies to be activated more quickly than they would be normally without having to go in and reset the BGP and the TCP connection. It's a kinder and gentler way of making these policies take effect. Let's go over to router R1. Let's see what router R1 would prefer to use when going to that backbone network. If everything is worked out correctly, the path via backbone 1, the BB1 router, it's going to be much less attractive than it was just a few moments ago. Sitting on router R1, let's do a show IP BGP command. Look at this. A few moments ago, remember that we preferred to go to a next hop address of 172.16.1.1, but now it looks less attractive. The path to get to that neighbor is through a couple of autonomous systems, not just a single autonomous system hop, it's two autonomous system hops. Therefore, notice the greater than sign, therefore, we are now preferring to go over the 2 meg link. We are preferring to go to router BB2 that has the next hop address of 172.16.2.1. That, my friends, is how we can use the autonomous system path prepend feature in order to influence path selection in a multi-homed environment. Just to make sure that this made it into our IP routing table correctly, if I do a show IP route, notice something. Notice that we're going to be getting to this backbone network 10.1.1.0. We're going to be getting there via 172.16.2.1. You know who that is? That's router BB2. Let's review where we've been in this lesson. In this lab, we took a look at BGP in a multi-homed environment. First of all, we did a basic BGP configuration for our core routers, routers BB1, BB2, and router R1. We specified the eBGP neighborships. We advertised network 10.1.1.0. Then with that basic configuration in place, we gave the show IP Bgp command from all of the routers running BGP to make sure that we knew about our neighbors. We knew that that network was being advertised via BGP, but we wanted to get that information into our remote side as well. To do that, we on router R1 redistributed the BGP learned route into RIP version 2. Finally, we had an issue, didn't we? We had an issue where we were using a suboptimal path to get to the backbone network. We were preferring, BGP was preferring, to go over a 1 meg link as opposed to a 2 meg link. How did we overcome that default behavior? We chose to overcome it using the Autonomous System Prepend feature, the AS Prepend feature, which allowed us to say it actually takes more than one autonomous system hop to get to this network if you go through BB1. We sort of exaggerated our position in the network by using that autonomous system prepend function. That concludes lab number 3, configuring multi-home BGP.